Assalamu alaikum and a very warm welcome again. We're going to be continuing with chapter number 4, part number 2. Now let's look at subtopic D5 on dynamic compaction. In cases where existing surface or near surface soil is of poor with regard to foundation support, field procedure known as dynamic compaction may be employed to improve the soil's property. This method is carried out essentially by repeated dropping a very heavy weight onto the soil from a relatively great height. The drop weight may be an ordinary wrecking ball, or it may be a mass especially designed for the dynamic compaction procedure. Typical weight range from 2 to 20 tons or greater, whereas dropping distance range from 6 to 30 meters. Generally, the heavier the weight and the greater the dropping distance, the greater the compactive effort will be. Now, for a given situation, however, the weight and dropping distance used may depend on the lifting equipment, such as crane available. So imagine you have your crane here. That's the wheels. That's the loading. Dynamic compaction may be used for both cohesive and cohesionless soils. It can also be utilized to compact buried refuse fill areas. In cohesive soils, the reduction of settlement due to dynamic compaction is more distinct than the increase in bearing pressure. The tamping produce a true pre-settlement of the soil well beyond the settlement that would have occurred as a result of construction weight only, without any preliminary consolidation. Now this statement is by Menard and Boyce in 1975. For cohesionless soils, dynamic compaction densifies loose soil. Dynamic compaction should not be done by dropping weight randomly. So you gotta think before you drop something. Instead, a closely spaced grid pattern is selected for a given compaction site. Let's look at figure D10. So you have to prepare such pattern before making a decision in dynamic compaction. Preliminary work is done to determine grid spacing and weight, height, and number of drops. Typically, 5 to 10 drops are made on each grid point, and figure D11 shows a photograph of the dynamic compaction site. Now this is where you have a pretty large area, and this one has some access to that site. That's where dynamic compaction can take place. The approximate depth of influence of dynamic compaction, D, may be determined in the terms of weight and distance drop. So there's a relationship, a simple one, between the depth, the weight, and the distance drop. Okay, if you draw it, distance drop, the weight, and the depth, it goes down under. Now there are two equations. The first is for cohesionless soil given by Leonard's, which is equals to this. And secondly is for cohesive soils from Menard and Boyce, given by this equation. These equations give the depth of zone D receiving improvement in meters if W in the metric tons and in H in meters. Please take care of your unit. The extent of improvement is greatest near the surface and diminished with depth. Improvement increases with the number of drops made up to some limit, typically from 5 to 10 drops. Beyond with additional drops, little or no additional improvement. With saturated, fine-grained soils, satisfactory result may be obtained by performing a series of drops at interval of 1 or several days. The purpose being is to provide time for dissipation of pore water pressure created by the previous compaction. It should be noted that the soil surface may become cratered as a result of dynamic compaction. This is particularly true for loose soils. When this happens, the craters must backfill and compact by other means. Craters is like a surface of the moon being hit by an asteroid. Now let's look at D6 InPlace soil unit weight test. Now after a fill layer of soil has been compacted by the contractor, it is important that the compacted soil InPlace dry unit weight be determined in order to ascertain whether the maximum laboratory dry unit weight has been attained. So after the dynamic compaction, you need to find out the properties of the soil after compaction. If the maximum dry unit weight has not been attained, additional compaction effort is required. It's pretty simple. There are several methods of determining InPlace unit weight. As a general rule, the weight and volume of an InPlace soil sample are determined from which unit weight can be computed. Measurement of the sample's weight is straightforward, but there are several methods for determining its volume. For cohesive soils, a thin wall cylinder may be driven into the soil to remove a sample. So that's your site, and you need to excavate this. This method is known as density of soil in place by drive cylinder method, and is designed as ASTM D2937 or AASHTO T204. The drive cylinder method is not applicable for very hard soil that cannot be easily penetrated. Neither it is applicable for low plasticity or cohesionless soils which are not readily retained in the cylinder. So you go back to the nature of the soil and think whether this test can be done on site or not. You can read this step by step. Okay, this is the apparatus used for determining the unit weight of soil at site. Okay, so basically I'm just going to draw this. Okay, that's your site. You're going to dig this. Okay, however, you don't know the volume. You take this to the lab and you can determine its other parameters such as moisture content, okay, and its unit weight. Okay. Oh no, you can't determine its unit weight because you don't know the volume. So you have another apparatus, okay, which has a standard sand properties. They call it Ottawa sand. Okay, this one. Okay. Now this is the standard that has a density of unit weight of 16 kilonewton per meter cube. So you're gonna have a standard sand. Okay. This one, you know the unit weight and you know the moisture content. Now the problem is the volume at site you don't know. So you're going to fill the Ottawa sand inside this, and then you can get the volume of Ottawa sand being filled inside this hole. So by having the volume, moisture content, you can calculate for unit weight of soil at site. Okay. So you have soil on this side and standard sand on this side for comparative study. So another method for determining in situ dry unit weight is known as unit weight of soil in place by rubber balloon method. It uses the same concept to find the volume, but this one uses a balloon with water inside. So you're going to pump the water so that the water will fill the balloon and it will occupy the excavated soil at site. Okay, the same concept with the first method. Okay, now although widely used, the sand cone and rubber balloon method are destructive testing methods, in that a sizable hole must be dug in the ground or compacted field. They are fairly time-consuming. A significant factor means numerous tests must be performed as quickly as possible at a construction site. Now let's look at a simpler approach, which is nuclear apparatus approach. So this is a non-destructive method for determining in situ dry unit weight. In use, this apparatus is placed on the ground or compacted field and emits gamma rays through the soil. Pretty easy. Some of the gamma rays will be absorbed, others will reach a detector. Through proper calibration, nuclear counts rate received at the detector can be translated into values of soil unit weight. Calibration curves are normally provided by the manufacturer. The nuclear apparatus also determines moisture content by emitting alpha particles that bombard a beryllium target, causing the beryllium to emit fast neutrons. Fast neutrons that strike hydrogen atoms in water molecules loses velocity. The resulting low velocity neutrons are thermal neutrons. So this is a nuclear moisture density apparatus. Very simple. You go to a site, let's put on a surface, and it emits some gamma, and whatever comes in will be determined by the value here. So you get unit weight from here. So this is a schematic diagram of how it works. Okay, so this is a soil surface apparatus, and this is some rod going down here, and the emission of rays. And whatever is detected is given by this value over here. So you can easily get your unit weight measurement. Pretty simple. Now what's the disadvantage of this? It has the disadvantage, however, of potential hazards to individual handling radioactive materials. The nuclear apparatus is also considered more costly than the apparatus used in the two methods. Okay, one method using the cone replacement, second using the balloon, third is using the nuclear approach. Now, in addition to determine in-place weight unit weight of soil, so if determine unit weight of soil, it is necessary to determine the soil's moisture content in order to compute the compacted soil's dry unit weight. Although the moisture content can be determined by oven drying, this is what you've done earlier, this method is often too consuming because test results are commonly needed quickly. So you need 24 hours for oven dry. Drying of soil sample can be accomplished by putting it in a skillet and placing the skillet over the open flames of a camp stove. So this is at site. The speedy moisture tester can also be used to determine moisture content quickly with fairly good results. Because of the rather small amount of sample utilized in this test, the speedy moisture tester may not be appropriate for use in coarser materials. So it goes back to the nature of the soil. So this is your speedy moisture tester. Now let's move on to subtopic D7 on field control of compaction. How do you actually know whether the compaction site is sufficient after compaction or reach its performance? Now, as related previously, after a field layer of soil has been compacted, an in-place soil unit weight test is usually performed to determine whether the maximum laboratory dry unit weight has been attained. After compaction comes your approach to determine unit weight. It is common to specify a required percent of compaction, which is the required in-place dry unit weight divided by the maximum laboratory dry unit weight expressed as percentage in a contract document. Thus, if the maximum dry unit weight obtained from ASTM or AASHTO compaction in the laboratory is 100 lb over feet cube and the required percent of compaction is 95% according to the contract, an in-place dry unit weight of 95 lb over feet cube or higher would be accepted. So this is written in the contract document. In theory, this is simple enough to do, but there are some practical considerations that must be taken into account. For example, the type of soil or compaction characteristic of soil taken from borrow pits may vary from one location to another. Also, the degree of compaction may not be uniform throughout. Some you get 95, some 100, some 80. To deal with the issues of non-uniformity of soil from borrow pits, it is necessary to conduct ASTM or ash-to compaction tests with the optimum moisture content for each type of soil encountered in a project. Then, as soil is transported from the borrow pit and subsequently placed and compacted in the field area, it is imperative that the result of each InPlace soil unit weight test be checked against maximum laboratory dry unit weight of the respective type of soil. To deal with the problem of the variable degree of field compaction of a soil, which was 95, 100, 90, it is a common practice to specify a minimum number of field unit weight tests. For example, for a dam embankment, it might be specified that one test be made for every 1,832.5 meter cube of field place. So every meter cube of this area, you need to do one test. So this is by a statement. To ensure that the required field unit weight is achieved by the field compaction, a specification contact between owner and the contractor is prepared. Now you're talking about an owner and also the contractor doing that compaction test. The contractor will normally specify the required percent of compaction and maximum number of field unit weight tests required. Let's say I want 100%. For compaction adjacent to a structure, where settlement is a serious matter, a higher percent of compaction or a higher minimum number of tests may be specified than for compaction. For example, of the foundation of a parking lot. The specification contract may also include additional items such as the maximum thickness of loose leaf, prior to compaction, method to obtain maximum dry unit weight, method to determining in-place unit weight, and so on. So you as a client or as the owner needs to be well versed with the characteristic or detailed properties on compaction tests so that you can channel the information to the contractor so he will do it accordingly. If you want 100%, the contract must do 100%. If it's less, let's say 95, do it again until you reach 100%. So bind it in a contract. As the owner's representative, an engineer is responsible for ensuring that the contract provision area carried out precisely and completely. He or she is responsible for the testing and must see that the required compacted dry unit weight is achieved. So usually, if the owner is not a geotechnical engineer, he will have an engineer to sort this out, which is you. An engineer will liaise with the contractor. So we have 3% here. If a particular test indicates that the required compacted dry unit weight has not been achieved, he or she must require additional compaction effort, possibly including an adjustment in moisture content. In addition, he or she must be knowledgeable and capable of dealing with field situations that arise that may be beyond the standard procedure. Now let's look at D8, soil stabilization. So D4 to D5 describe a physical means, field and dynamic compaction, whereby a soil that can have its physical properties improved to increase bearing capacity, increase shear strength, decrease settlement, and reduce soil permeability. Soil stabilization can also be used to improve the properties of a natural soil by preloading the soil or by adding other special soil. So you have preloading or adding chemical material or some of fabric material to the soil. So there are many ways to stabilize the soil. Preloading is carried out simply by adding fill or other surcharge to the natural soil in situ and allowing the added weight to consolidate the soil naturally over a period of time. In general, the greater the added surcharge and the longer the time it is in the place prior to construction, the better consolidation will be and the better the bearing capacity of the soil will be. In most cases, the amount of material to be used as surcharge and the time available may be limited, however, by practical or economic consideration. Transporting soil is expensive, and in some cases suitable surcharge material may be not readily available. The time needed to effect soil improvement may be reduced by including vertical sand or gravel drains in the soil during surcharge period. The amount of time needed varies from several months to several years. Preloading works best in soft, silty, and clayey soils. Granular soils, where consolidation is an insignificant phenomenon, are not generally amenable to improvement by preloading. So this is a preloading procedure where you have a total of 2.5 meter of preloading at site. So this is the site original grade. Next is on mechanical stabilization. Now this is relatively simple means of soil stabilizing that is carried out by adding soil material to the natural occurring soil. The added soil material is usually mechanically mixed with the natural soil and worked together, after which the mixture is compacted. Normally, a blending of coarse aggregate, fine-grained soil is achieved in order to get a soil mixture that poses some internal friction and cohesion and will thereby be workable and subsequently stable when mixing and compaction has been completed. So you prepare this, dump it at site, and compact again. The third one is chemical stabilization. Now this is achieved by adding cementing material or some kind of chemical to the soil. The chemical material may be mechanically mixed with natural soil and the resulting mixture compacted. Again, the same procedure with the mechanical stabilization, but this one they use chemicals. The chemical material may be simply applied to the natural soil and allowed to penetrate the soil through void space. Another process is to inject the stabilization chemical into or through the soil under pressure. This is known as grouting. The procedure of grouting is generally performed where it is necessary to improve soil that cannot be disturbed. Grouting and injection stabilization are generally performed by specialty contractors who have proper and adequate equipment and have developed experience over the years with one or more stabilization procedures. So this is the types of chemical that can be added, including various kinds of cements, so the most important statement here, geotechnical engineers' practical experience may be invaluable in deciding what specific type of chemical stabilization to use in any given situation. So that's the chemical. Just spread it in the soil and it will have some reaction to stabilize. Now the fourth stabilization is by using geosynthetics. So this one refers to a family of manufactured materials, sheet or net-like products made of plastic or fiberglass. Geosynthetics may be used to stabilize and reinforce soil masses, such as erosion control, or a slope surface, reinforcing backfill or retaining wall, reinforcing slope or embankments, slope protection of open channels, and drainage control. So figure D19 illustrates a number of examples of the use of geosynthetics. So it may come in the form of GeoTextile, Geogrids, Geonets, and Geomembranes. So if you look at this figure, A is the geotextile stabilization, B is the geocomposite drainage panel, C is a high geotextile slide repair. D, Geogrid reinforced steepened slopes. And E, geosynthetic clay liner. Not so clear, but I'll give a better photo in the next slide. GeoTextile are similar to woven fabric or textile. Common usage of geotextile for strata separation, soil reinforcement, filtration, and so on. In strata separation, the geotextile is simply placed between two different soil strata where it serves to retain the strata separation and to preserve each stratum's individual properties and function. This is when you have layers of soil and the layer is separated by geotextile. So this is strata separation. A typical example is to place a geotextile between a fine-grained substrate soil and aggregate base course to prevent the fine-grained soil from intruding into the aggregate base course. So the coarse is here and the fine grain is here. You have your separation in between. In reinforcement, the geotextile may be placed over a weak soil with a layer of good fill placed on the geotextile. In filtration, small opening in the geotextile allows water, but not soil particles, to move through the geotextile. 1, 2, 3. For example, a geotextile may be used in this capacity to protect a drain from soil infiltration. So this is a geotextile. Now let's look at Geogrid. So they have larger openings. So these are the sizes. Then the geotextile and therefore resemble nets. It's like fishing nets. They are used to reinforce relatively poor soils over which paved surface as roads and parking lots are to be constructed. Geogrids can be used for improving slope stability, to prevent potential slip failure, and also as a reinforcement to construct earth wall similar to reinforcement wall. So larger opening compared to the first one. So the first one was geotextile, and then move on to Geogrid with larger openings. Third one is Geonets. Similar to Geogrid but have intersecting ribs. They may be used for drainage purposes under roadways and landfills and behind retaining walls. They too often used in conjunction with geotextile. Geonets are usually installed on a slope towards a perforated drain pipe or a ditch. Okay. So this is the third one, Geonets. We also have geomembranes, which are impervious, thin plastic sheets. They are used to prohibit or greatly restrict the movement of water within the soil mass. A common example of their use is as landfill liners to prevent the movement of wastewater from within the landfill into surrounding strata. So if you have your landfill, rubbish inside, so this is the geomembranes. Just like this. So that's all about it for chapter number 4 on soil compaction. The design pad is coming up next. So have a good day and finish your design pad, and see you next time in chapter 5. Thank you very much.